Unit 7, right? CHEM, organic chem. Now, this is not on exam number 2, right? This is the first topic for the next exam. Okay, organic. Organic chemistry. Probably won't need your calculators on exams 3 or 4. It's a lot of memorizing. Organic chemistry historically was once defined as the study of the structure and function of molecules that originated from living organisms. It had to come from something living in order for it to be organic in nature. That would be as opposed to something from mineral sources. Then the molecules that were once isolated from living organisms began to be synthesized in a laboratory environment in what we call in vitro in the lab, as opposed to in vivo in the body. So now these molecules could be synthesized, and so we had a new definition for organic. Organic chemistry is the study of the structure function and properties of compounds that contain carbon. Whole area of chemistry devoted to a single element, carbon. Many people define organic compounds by the obligate presence of both carbon and hydrogen. Not a big deal, but theoretically, very strictly theoretically, it's carbon. Carbon is organic. It is arguably the most complex and mysterious of all the areas of chemistry. We have biochemistry, inorganic, analytical, organic chemistry, and physical chemistry. Organic is the one that seems to be the most mysterious. If you take a look at carbon, okay, carbon can do some unusual things. Now we know that it is in group 4. So if we look at its Lewis structure, we see 4 electrons, which means we can form 4 bonds, right? 4 bonds. Now, one of the underlying rules in organic chemistry is maintaining the tetravalency of carbon, which is basically translated to say carbon wants 4 bonds. Okay, it can take different numbers of bonds, but then it'll take charges. Okay, so we're going to maintain or make sure that carbon has 4 bonds at all times. But carbon, unlike many other atoms, can do some cool things. It can bind to itself in huge chains, huge chains, thousands of carbons long. So you can have carbon with 4 single bonds. You could have carbon, I'm going to go ahead and bind it to itself. Okay. You can have carbon with double bonds, and you can have carbon with triple bonds. But notice in each case, every carbon always has 4 bonds. 1, 2, 3, 4. This carbon has 1, 2, 3, 4. Over here, this carbon 1, 2, 3, 4. This one, 1, 2, 3. So it can do some pretty remarkable things. Bless you. Okay. Now, the study of organic chemistry doesn't involve the individual study of the hundreds of thousands, if not millions, of organic compounds out there. Instead, we break up classes of organic compounds based on certain structural features or groups of atoms that all members of a class have in common. And we call these functional groups. Functional groups can be an atom, it can be groups of atoms, it can be structural features, that classify a particular atom into a particular organic class. So atoms, groups of atoms, structural features used classify organic molecules. And these are common to all members in a particular class. Now, in most cases, the functional group dominates the reactivity of the molecule. Okay, it dominates the chemistry of the molecule. So, regardless of what else is going on in the molecule, if you see that functional group, it can undergo predictive chemistry and allow you to make some sort of prediction on chemical behavior. For example, okay, i.e., and we'll see these today. Carbon-carbon double bond belongs, any molecule that contains a carbon-carbon double bond belongs to the alkene class of organic compounds. And in most cases, that double bond will dominate the reactivity of that particular molecule. So by studying the structure and the function of the carbon-carbon double bond, you can gain knowledge on thousands and thousands of organic compounds. So the functional group approach is by far the most effective way to look at organic chemistry. And of course, that's the way that we'll approach it as well. Okay? Any questions? Okay. Now, there's a lot of memorizing that you're going to have to do in these chapters, in these next units. Okay? Each functional group, and there's a list of them. There's a list of them in Table 7.1. Each one of those functional groups has its own protocol for naming and its own endings, its own reactions. So you have to be able to recognize those functional groups and then know how to name them. And we're going to go through them individually. I'm going to give you the naming protocols. I'm going to show you how to approach the organic portion of chemical nomenclature. But it's going to be an awful lot of memorizing on your part. Okay? Now, there are some other elements that are found commonly in organic compounds. The halogens in group 7, fluorine, chlorine, bromine, and iodine. You see some nitrogen. You see oxygen, of course, carbon, and hydrogen. So it's not just, organic compounds are not just limited to carbon and then carbon and hydrogen. Most of the time you find other different types of atoms attached as well. Okay, let's look at our first class of organic compounds, the alkanes. The alkanes. The alkanes are saturated hydrocarbons with a general formula of CnH2n plus 2. So there's three things in the definition of an alkane. First of all, it needs to be saturated. Secondly, it needs to be a hydrocarbon. And thirdly, it needs to satisfy its general formula. If it is saturated, that means it contains only carbon-carbon single bonds. There are no double or triple bonds in the alkane class. So, saturated means it contains only carbon-carbon single bonds. Saturated. Hydrocarbon means it contains only hydrogen and carbon. Contains only hydrogen and carbon. So if you had a formula, for example, that looked like this, okay, even at the very beginning of our study of organic chemistry, you know that that's not an alkane because it's got a Cl in it. It's an alkane derivative. It comes from alkanes, but it's not in and of itself an alkane. Okay. Now, there are 10 alkanes that you have to memorize. There's no way around it. This is where naming starts. You must memorize the first 10 alkanes listed in your book. I will write them down over here. We're going to run out of room. These are the first 10 alkanes. And notice that the names of the alkanes all end in A-N-E, just like the word alkane. Notice they all end in A-N-E. Methane, ethane, propane. This is the same propane that's in your grill. Butane, that's the same butane in those cheap Bic lighters. Pentane, hexane, heptane, octane, that's the gasoline additive, or gasoline. This is nonane, not nonane, it's pronounced nonane, and then we have decane. Now the molecular formulas are easy to remember because the only one you have to remember is the first one. Methane is CH4. Methane is CH4. Each successive formula, each name, or the formula for each successive alkane, you increase the carbon by 1. So here was 1, we make this one 2, this one 3, this one 4, 5, 6, 7, 8, 9, 10. We increase our carbon by 1. Now, once you get to penta, the prefixes tell you how many carbons you have, right? Penta, 5, hexa, 6, hepta, octa, nona, deca. Those first 4 are a little unusual. And you increase the hydrogens by 2. So it becomes 6, 8, 10, 12, 14, 16, 18, 20, 22. These are the molecular formulas and the names for the first 10 alkanes. Everybody see? You have to memorize these. Okay, you have to. You have to. Because you have to know that a 5-carbon chain is pentane, or pentane derivative. We'll see later on that a 5-carbon chain alcohol will be pentanol. A 5-carbon chain carboxylic acid, pentanoic acid. 5-carbon chain aldehyde, pentanol, Al. Okay, so they're all named from these basic skeletons. So this is where your naming starts. This is where it begins, memorizing those first 10. All of our other protocols will actually just be little tweaks of these, of naming substituted alkanes. So let's see if they all satisfy our definition. In our definition, we had to be saturated. We don't really know if they're saturated because we don't really know the bonding arrangement, right? We can't really tell yet by looking at it if we have a double bond or not. That's a tough one. So let's wait, put that one aside. Do they contain only carbon and hydrogen? Yes, they do. Do they satisfy the formula CnH2n plus 2? Yeah, they do. Example, C4H12. If N is 4, then the number of hydrogens must be 2 times 4, 8 plus 2, 10. Did I do that wrong? See, I copied it. 10. Right? 2 times 2 is 4 plus 2 is 10. So this is our formula. I don't know where I got C4H12 from. So they all do. If you take the subscript attached to the carbon and you multiply it by 2 and then add 2, you should have the subscript attached to the hydrogen. So 12, 14, 14 plus 2, 16, 16 plus 2, 18. So yes, it does satisfy the general rule. If you are a hydrocarbon, if you contain only carbon and hydrogen, and you satisfy this general formula, you will be saturated. It will contain only single bonds. So there's some redundancy in the definition. Okay? You could either say that it's a saturated hydrocarbon, or you could say a hydrocarbon obeying that general formula. Because saturated and that formula are the same thing. They say the same thing. All right, everybody see? You gotta memorize it. It starts right here. You gotta know 4-carbon chain butane derivative, 5-carbon pentane derivative. Okay, so there's a number of different ways to represent organic compounds, and we already know one of them. It's right there, the molecular formula. There are different ways to represent organic molecules. The first one that we're most familiar with, and that we've seen already in our study of intro chem, was our molecular formulas. There's also a structural formula. So how do we represent molecular formula? Now, each method, has advantages and disadvantages. Okay? Some are easier but don't give you quite as much information. Some are more tedious, and for the amount of time it takes to write it, the amount of information isn't often justify the amount of work. So our molecular formula, i.e., let's stick with butane. Now, this is very easy to write. It's very compact, but it doesn't tell you anything about the bonding arrangement. It doesn't tell you which elements are bound to which, what the connectivity of the elements are. So it's quick, but it gives us no information at all about what the structure might look like or the bonding. Next, we have our structural formula. Now, our structural formulas, our open structural formulas, are drawn by first looking at the number of carbons. Let's again look at C4H10. What you're going to do is you're going to connect your carbons in a straight continuous line. You're going to make sure that you maintain the tetravalency of carbon. Make sure that every carbon has 4 single bonds to it. 1, 2, 3, 4, this carbon. 1, 2, 3, 4, this one. 1, 2, 3, 4, this one. 1, 2, 3, 4. So all of these carbons have 4 bonds, and they're all single bonds. We're simply going to fill in our bonds with hydrogens. We're going to fill in our bonds with hydrogens. And we see that this is C4, 1, 2, 3, 4. That's C4H. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. H10. This is the formula for butane, the structural formula. Now, the advantage of the structural formula, obviously, it shows you the sequence of bonding. It shows you that the carbons are bound to each other and that some of the carbons are bound to 3 hydrogens while others are bound to 2. So it actually gives you details about how the bonding occurs with that particular molecule. So this is very valuable. It gives us some very valuable information. The next one is the condensed structural formula. This will probably end up being your method of choice. Okay? The condensed structural formula is easily obtained from the open structure The condensed structural formula would look like this. And you can see here, this is where the CH3 comes from. This is where the CH2 comes from. Alternatively, you can see another representation where they actually just put the bonds in between them. Okay? It's somewhat arbitrary. Neither one is better than the other. Sometimes they show the bonds in here, sometimes they don't. Now, in this method, it's understood that the hydrogens are bound to the carbon that they follow in the formula. So when you see this, you see the carbon, anything that follows that carbon until you get to the next carbon is bound to that carbon. So this one has 3 hydrogens. There's the next carbon. So anything in between there is bound to this one. Anything in between these 2 carbons is bound to this one. You're going to see that later. That has value when we start substituting heteroatoms in there. When we start putting chlorines and bromines in here, for example. You might have CHCl. You know that that Cl is bound to the carbon that it follows. Okay, so in this particular method, it's understood that whatever follows the carbon is bound to it until you hit the next carbon. This one kind of mixes our molecular formula with our structural formula because it allows us the convenience and the quick, easy way to represent the bonding configuration around each carbon. So it gives us a little bit of both. It's kind of nice. Like I said, this will probably be your method of choice when you're just beginning to become familiar with how these things are represented. Okay? The last method is called the line formula. Sometimes it's also called skeletal. Okay, the line formula, when you're using this method, carbons and hydrogens are never written. So the one for butane, the line formula for butane would be carbon 1, 2, 3, 4. That would be butane. I know that it's unusual. Using this method, carbons and hydrogens are never written. And it's understood that at the beginning and end, there's a carbon. And at each change of direction, at each peak or valley, there's a carbon. It's also understood that the carbon's tetravalency is filled with the appropriate number of hydrogens, which again are never written. So if you look at this, the things that aren't written, you understand that there's a carbon here, 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 and here. And that each carbon in itself has its tetravalency filled by hydrogen. So see this carbon here, it's already got 2 bonds. 1 to each of the adjacent carbons. So it only has 2 more. Okay? These are understood and therefore never written. Don't write them in here. If you use the line formula, it's incorrect to write them in here like I just did. I'm just doing it to show you visually where those carbons are. This is probably the method of choice for most organic applications because that's unfortunately how the software is. This is how the software writes it out. Okay? The next time you get sick, okay, God forbid, and you have to go and get some medication, when you go to pick it up from the pharmacy, open up the medication. They always have these little inserts inside. If you open up the insert and you look at the actual structure, it's almost always given in this line formula method, using this method. It's kind of cool. They can get really complex, but you can see it. That's butane, believe it or not. Now, as we progress through our study of OChem, you will become more familiar with this. Okay, because when we talk about cycloalkanes in a little bit, they're almost exclusively represented using the line structures. So you'll become familiar with them. Okay? This is like learning a whole new language. It really is. It's like learning a whole new language, right? And since this is our first lecture on it, you really have to start with that right now. You have to start memorizing our quote-unquote alphabet. You'll see how important this is. right? There's so many new terms that are going to be coming at you. And unfortunately, we spend our whole time, chapters, units 1 through 6 or whatever, telling you, look, be deductive in your reasoning, your approach to problem solving. We want you to use critical thinking skills. We want you to know the process and how you got from the starting, given information to the end. And it's critical that you understand how to solve the problem. And then you get into organic chemistry, and unfortunately we have to say, that's just the way it is. Right? Why is it 4-carbon chain called butane? Because that's the way it is. Okay? Why does hydrating an alkene make an alcohol? That's the way it is. Okay? And it presents to you a basic conflict. All right? Because you want to know why. But this stuff, we know why. We know why. Like I was there, like we discovered it together. But chemists, academia, we know why these things happen. But there are some things that we don't. So you get to some reactions and you study them and you say, gee, I wish I could tell you why that happened. But not only do I not know, research hasn't uncovered the mechanism that produces this product. We think it's this, we think it's that, but we don't know for sure. Okay? So, there's going to be a lot of memorizing. And those of you that hate math, which I know you do, so there's always people in here that hate math. I'm really good at memorizing. Be careful what you wish for, because you got it now. You've got your memorizing now. Alright? Okay. These different representations. Unfortunately, on the exam, I can't tell you which one will be, partial. Which one will be represented. You can see one question in line formula. You could see one in condensed structural formula. You could see one in structural. You more than likely aren't going to see it like this, though, for the reason that we're going to talk about right now. Okay? You'll get a favorite, but don't close the door to the other ones. You're going to have to know them all. Okay? It's okay to get a favorite, but make sure that you stay open. Okay. The reason why you probably won't see a representation given in the molecular formula is because the molecular formula can give you a number of different types of compounds. Now these are called isomers. Isomers. Notice I'm calling it molecular formula because organic compounds are molecular. There's no metals, right? These are all covalent. They have the same molecular formula, or you could alternatively say chemical formula. But they have different blanks, okay? That's because the name of the isomer will tell you what the difference is. For example, structural isomers. Structural isomers will have different structures. Conformational isomers will have different conformations around a carbon-carbon bond. Newman projections, we call them. Geometric isomers. These have different geometries. We'll see those today. Cis and trans. There's so many different types. Positional isomers. Structural isomers. Like I said, constitutional isomers. Stereoisomers. There's a lot of different types. When we use the term isomers in here, we're primarily talking about structural isomers. Okay, structural isomers. So let's see how we determine structural isomers. First, I want to give you an example. Let's say that we look at I'm going to run out of room. Alternatively, there's our line formulas. Now, the one thing the line formulas do, and these are model kits. This is a model kit. And if you're going to study organic chemistry, you absolutely have to have a model kit. One of the inherent difficulties is trying to present a three-dimensional science on a two-dimensional blackboard. Those are one of the inherent difficulties. We'll provide you with model kits for the exams or quizzes if you want one. But one of the things that the line formula does, and for my model kit here, clip them together, my carbons are here in the center, and you see that I have 4 bonds coming from each carbon. So I'm going to make butane for you. And incidentally, anything you can do with this model kit, you can do in real life. So these bonds are vibrating in this constant kind of motion, right? So if you look at butane, all right, one thing about the line structure, if you see the backbone here, it gives you very realistic bond angles. Okay, it gives you a real good geometry, actually, of what the actual molecule looks like. So if I look at this, what's the formula? 1, 2, 3, 4, H610, right? C4H10. What's this formula? C4H10. They have the same formula, but clearly they are different structures. These are isomers. They're isomers. More specifically, they're structural isomers. Like I said, when we say the word isomer in the book, we mean structural isomer. It really should say structural isomer every time, but it doesn't. Okay? Everybody see that? What an isomer is? How do we get them now? How do we get an isomer? Well, the first thing we do is we have to have a formula, a question, right? So the question would say, write or draw isomers of C4H10. So we have a starting point. The first thing we do is we write down the structure that has that number of carbons in a straight non-branched chain. 1, 2, 3, 4. There it is. I'm not going to write in the hydrogens yet. I'm going to write in the hydrogens after I have all of my isomers. In order to determine how many isomers exist now, we have to cut our chain length by 1 carbon. We cut the chain length by 1 carbon, and then we take that 1 carbon and we put it at every other carbon. So, here's 1. There's 2. There's 3. You see how I just took that carbon that I cut off here and I just moved it down the chain? See that? I cut my chain length again and I have 2 carbons. Once you're halfway to the beginning or given number of carbons, you don't have to do it anymore. All you're doing is reproducing something that you've already drawn. So I started out with C4, I went to C3. I don't have to go to C2 anymore because it's halfway. Okay, does everybody see that? So if you had 6 carbons in your chain, you would cut your chain to, you'd start with 6, then you'd cut it to 5, then you'd cut it to 4, then you wouldn't have to do 3 because that's halfway. So I don't have to do C2. I look at this now and I count my longest continuous chain of carbons. 1, 2, 3, 4. Any of these forms that has a continuous chain of carbons of 4, I've already got it. Here it is. It might not look like it, but I do. 1, 2, 3, 4. I've already got that one. I didn't say it had to be straight. It's just got to be continuous. 1, 2, 3, 4. 1, 2, 3, 4. These are the same things, right? This one looks like that. Nice and straight, right? This one could look like this, with the first one up. Okay? 1, 2, 3. 1, 2, 3. 1, 2, 3. I don't have one with 3. I don't have one with 3. 1, 2, 3, 4. Got that one. Okay? Don't trust your lying eyes. Alright? Don't trust them. Believe it or not, this one, and this one are identical. They're the same thing. The only one that's different is this one right here. So now I can go through and I can put in my hydrogens. Again, all I'm doing is maintaining my tetravalency, making sure that all my carbons have 4 bonds. And we can already tell that this is the structure that I just had previously. I think I wrote it a little differently, but there it is. And this is what we have. Okay, you can verify that these are the same things. Here's my CH3. Here's a CH3, right? That's the one goes right here. Here's a CH3, and that H is behind or following that carbon because it has to be attached to that carbon. Everybody see how to do them? Everybody good? Again, memorize, memorize, memorize. All right. So how do we name our alkanes? You have to be familiar with the protocol for naming alkanes because all of our other naming protocols are derived from it. Okay, it's just a little tweak here, a little tweak there. So we have to know how to do these. This requires some memorization, but pretty soon you're going to be, because you're just going to practice naming so many compounds that it'll almost become second nature to you. Okay, we are going to use IUPAC naming protocols, International Union of Pure and Applied Chemistry. For alkane naming, now I left these up here on purpose because we're going to need them right now. Alkane naming. Or alkane nomenclature. First of all, you have to determine the longest continuous chain of carbons. That's first. Notice that it does not have to be straight. That's what's going to throw you. You're going to have a chain going all over the place. It doesn't have to be straight. It's just continuous. Identify and name any substituted groups that are attached to number 1. You're going to identify them and name them. Anything that's hooked on to the longest continuous chain. We're going to number our carbon chain. We're going to call it the parent chain, because we're going to name it based on that longest continuous chain. We're going to number the parent chain. Such that the first point of substitution takes the lowest number. You'll see from an example. Locate substitutions. Using the number on the carbon they are attached. Lastly, we're going to name it. Lastly, we're going to name the molecule. Now, there are little things that we're going to have to add to this, but this is where we're starting. Okay? Now, the first substituted compounds we're going to look at are hopefully halogenated compounds, because that's where I'm starting. started with alkyl. We start with halogenated. When we saw fluorine, chlorine, bromine, and iodine in inorganic nomenclature, remember binary compound? They ended in IDE. It was fluoride, bromide, chloride, and iodide. That's not so in organic nomenclature. Fluorine is fluoro. Chlorine is chloro. Bromine is bromo. And iodine is iodo. Iodo. We're running out of board, huh? Let's take a look at one. I'm going to erase this just so I can get some more room here to write. Let's start out with an open structural formula. Okay? Alternatively, this would look like that. See how we have the CH3 here, then we have the CH and Cl, CH2, CH2, CH3. First thing we have to do is determine the longest continuous chain of carbons. For this, we can see it. It's a straight chain, right? 1, 2, 3, 4, 5. 5 carbons. You know what that makes it? A pentane derivative. It's not pentane, because pentane would require it that it contain only carbon and hydrogen. And we see the chlorine here. So it's not an alkane. It's an alkane derivative. But it is going to be named as a pentane. Identify and name any substituted groups. We only have one. There it is. It's chloro. Now, I want to number my carbon chain in such a way that I put the lowest number on the first point of substitution. We only have one point of substitution. When you have your carbon chains, you're going to number them this way or you're going to number them that way. All right? If I number them this way, left to right, I'm going to number my carbons 1, 2, 3, 4, 5. If I number it right to left, 1, 2, 3, 4, 5. If I number it right to left, that puts my chlorine on carbon number 4. If I number it left to right, which is in green, it puts my chlorine on carbon number 2. So I choose the left to right, the one that put it on 2. Sometimes people say you number from the end, you find the substitution closest to the end, and you number it from that side. So you could look at this substitution and you can say, oh, it's closest to this end, so I'm going to number it from that end. That's another way to look at it. So this is two dash chloro pentane. All one word. I locate the carbon or the chlorine, the substituted group, by using the carbon that it's attached to. So what this says is, I have a pentane, 5-carbon chain. At carbon number 2, I have a chloro. Everything else is hydrogens. Okay? Does everybody see that? Yeah. All right. What is that? 3-bromopentane. Everybody get that? Yeah, easy, come on. Easy. Longest continuous chain of carbons, 1, 2, 3, 4, 5. 5 again. Makes it a pentane again. I didn't do that on purpose. No matter which side, I have one substituted group, it's bromo. No matter which side I number from, it still comes out on carbon number 3. So it doesn't matter which way I number. This way or this. 1, 2, 3. 1, 2, 3. This is 3-bromo pentane. What is it? 2-fluorohexane. Yep. Everybody got 2-fluorohexane? This time we're going to number from this side, right? 6 carbons makes it a hexane derivative. It can't be hexane because it's got a fluorine here. And hexane is an alkane, which means it's a hydrocarbon. It only has hydrogen and carbon. But it is a hexane derivative. So this is 2-fluorohexane. Okay? Everybody good so far? keep writing those pentanes for some reason. I don't know. What's different about this one? We have 2 substituted groups on here now, don't we? We have 2. Everything is the same, except you alphabetize them. Everything is the same, except you alphabetize them. What is our longest continuous chain? How many carbons? I already told you it's 5, right? Which way are we going to number? This way or this way? Left to right or right to left? Left to right, that's right. Correct. All that matters is the first point of substitution. So if I number this way, 1, 2, that's it. It goes carbon number 2. If I number the other way, I don't see my first point until carbon number 3. You don't have to go to the same carbon. It's just the first point of substitution. Okay? So, if I number left to right in green, I have my first substituted group at carbon number 2. I have another one at carbon number 3. I have a bromo, right? I have a chloro. I need to alphabetize them. What do you think the name of this compound will be?
2-bromo-3-chloro.
Right. Sounded like she's talking another language, didn't it? She almost is. Right, these are getting bigger now, so I'm going to have to clear out some room here. This is alphabetizing. Bromine's coming first. So I locate bromine. 2-bromo. I still have more substituted groups. So I can't just say pentane. I have another substituted group at carbon number 3. Two bromo, 3-chloropentane. Okay, so we add a little down here. Instead of number 5 saying name the compound now, you could write multiple substitutions, alphabetize. You got to alphabetize them. I don't like writing all of that stuff because there's you know, we have to use prefixes or other things. I like starting very simple so that you can be comfortable with it and then adding to it. Okay? It's better to add to stuff that you're already comfortable with rather than write all of this and take up all the board. Going the other way, much easier when you're given the name in organic. It's much easier. I have a pentane. Watch this. That's how easy it is. I have a pentane. 1, 2, 3, 4, 5. At carbon number 3, I have a chloro. Carbon number 2, I have a bromo. Br, Cl. There it is. Fill in the rest with hydrogens. Now, it doesn't matter that I put the chlorine down here in this one and it's up there in that one. You have free rotation around those bonds. Okay? It doesn't matter if I take this in one structure, say that's a substituted group. It might be pointing up, right? It doesn't matter since you have free rotation and the molecule can rotate in space. Now it's pointing down. You have free rotation around those bonds. Now it's up. Now it's down. Now it's up. Now it's down. So it doesn't matter. Don't be confused by that. The only thing that matters is that it's still on carbon number 3. Okay? Now, the numbers don't matter. They don't have to be in any particular ascending or descending order. You don't care about the ascending nature of the numbers. The numbers serve only to locate substitutions. So if I swap these, and I put the bromine here, and the chlorine here, this would become 3-bromo, 2-chloro. Okay, the numbers don't matter. 2-chlorine, 3-bromo. The bromine comes first because it's first in the alphabet. Yes, it is. It's first in the alphabet. Okay? Everybody see that? Multiple substitutions, alphabetized. What if it's the same substitution? Someone want to take a crack at that one?
3,4-dibromoheptane.
3,4-dibromo.
Heptane.
2, 4, 6, 7. Yes. Again, someone's doing their work, aren't they? Did you guys get that?
You put like 3-4 or just
3, comma.
3? Okay.
Number in our chain. You look, you say, which way am I going to go? 1, 2, 3. I can stop. I don't have to go any further. 1, 2, 3, 4. If I go this way, my first substitution is at 4. This way, it's at 3, left to right. I'm going to use the red. I have 2 bromines. One is at 3, one is at 4. I name this 3,4-dibromo heptane. 7-membered ring, or sorry, 7-membered carbon chain will be heptane. Notice the prefix here, di, meaning 2. You don't do 3-bromo, 4-bromo. Everybody see that? What would happen if they were on, what do you think would happen if they were on the same carbon? Just a minute ago, they were on different carbons, and we had to specify the location of each substituted group by indicating which carbon they were bound to. This time they're bound to the same carbon. What is it?
Is it 3 degrees added for marking?
Yeah? It is. It's 3,3-dibromo. 1, 2, 3, 4, 5, 6, 7 heptane. IUPAC says you will locate substituted groups using the carbon that they're attached to, even if it's the same group on the same carbon. You don't say 3-dibromo. If you say dibromo, that means you have 2 bromines, you better have 2 carbons on there, even if it's the same carbon. Okay, you would never say 3,3-bromo, and you'd never say 3-dibromo. It's got to be 3,3. IUPAC doesn't care that they're on the same or different carbons. You have to locate them. Okay? Another modification to our naming, right? Right? So, we have the longest chain, we identify and name substituted groups, we number the parent chain. Okay? This is where it gets sticky, right? If we have multiple substituted groups, we alphabetize. If the substituted groups are the same substituted group, we use our prefixes. Mono, di, tri, tetra. That's as far as we're going to go, tetra. Locate
on
them
the first one too, right?
What's that?
It could be 1,1,1 tribromo.
Yeah. Heck yeah. Want to do bromo? One tribromo butane. Okay. See the importance of memorizing the alkanes? I mean, seriously. If you don't know those, I can't help you. I can't. There's nothing I can do. Okay? Again, this is either, I mean, you have to know this. You're going to know it or you're not. It won't come to you while you're staring at it. Yeah. Oh, I remember. It won't come to you. And unfortunately, names are either all right or all wrong, right? There's only one correct name. Now we're going to see there are a couple common names that you might see written differently on the exam. But by and large, you have a name, there's only one way to spell it, one way to say it. Anything else is wrong. But this is a multiple choice exam, right? So you don't have to spell the name, you just have to pick it out. Okay? All right. Unfortunately, we've been dealing with group 7 substituted compounds, right? Those are halogens, right? Group 7's halogens. So these were halogenated compounds. Some of the organic compounds are halogenated, but a vast majority of them are something a little different. So this is a great start, though. We got a good foundation. I'm not going to throw you any curves. Don't be looking at me like that. Okay? Most of the organic compounds that we see are smaller alkanes substituted on larger alkanes. This creates a problem for us because it creates what we call a branch point in our carbon chain. Okay? Let's take a look at methane. This is methane, CH4. This is CH4. Have it right here in my hand. And I purposely only labeled one hydrogen. Right? I can move methane around. I can manipulate this molecule in space, and I can make that white ball appear at any other position by simply moving it. So you want it here? Okay. Want it down here? Okay. Want it over here? Okay. If you can do that, if you can make the white ball appear at all of the other positions by simply moving the molecule in space, then the hydrogens are equivalent. They're identical. There's no difference between them. When you attach a smaller alkane onto a larger alkane, you have to remove a hydrogen to create a point of attachment. Right? So we have to get rid of a hydrogen here to create that point of attachment, whatever it may be that we're going to hook that onto. Right? And for methane, it doesn't matter which hydrogen you remove because they're all equal. Okay? But when I remove a hydrogen, I now have CH3, right? I have CH3, and then I have an attachment point where the fourth hydrogen was. So it's not methane anymore because methane is CH4. Right? So I can't call it methane. When you remove a single hydrogen from an alkane and create a point of attachment, we term this new group an alkyl group. An alkyl group. ALKYL. Alkyl group. If we take the word alkane and convert it into alkyl, how do we get it? We drop the ANE and add YL. We drop the ANE, see how we drop this? And add this. Converting the word alkane into the word alkyl requires that we drop the ANE and add the YL. We do the same with the name. We do the same for the alkyl groups. For methane, the alkyl group is CH3 with one bonding position open. We are basically making small alkanes substituted groups. We're going to make them substituted groups on larger ones. The name methyl. Notice how I took methane, I dropped the ANE, and I added YL, methyl. Everybody see? We treat them just like any other substituted group. See all the memorizing we got already? Right? A lot of memorizing already, right? Methyl, ethyl, propyl, butyl, pentyl, and they're all there. We treat them just like any other substituted group. So if I look at now, this gets a little sticky. Our first rule said we need to determine the longest continuous chain of carbons, right? We have to look at all possibilities. Because we read left to right, most of you are just kind of inherently drawn to that left to right, you know, that left to right chain. 1, 2, 3. Now I got a choice. I got a choice, and I got to look at both of them individually to determine what the biggest one is. 4. Stop. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. I got to look at all possibilities. Branch points in our carbon chain create issues for us determining what is the longest continuous chain, because we have to go down both roads. Okay? 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 6 appears to be the biggest one. You've got to look at all of them. Don't believe your lying eyes. Don't just automatically say, oh, the longest chain is left to right. It might be. It might be, but it might not be. So this is a 6-carbon chain. Other than that, everything is the same. Other than making sure that once we determine the longest continuous chain, everything else is the same. We have one group substituted. What's it called? Methyl. Methyl, right? Methyl. We number our chain the same way. What do we got? 1, 2, 3. If I go left to right, I got blue now. 1, 2, 3, 4. Oh, I don't want to pick the blue way. I want the one that gives me the lowest number on my first point of substitution. This is 3-methyl hexane. 3-methyl hexane. You treat the alkyl group just like any other substituted group. I was going to use that. You're wondering why I was going to just reuse it, but I'll just write another one. Okay, everybody good? Guys got names for it already? Yeah? Go ahead.
2-bromo, 4-chloro, 3-methyl hexane.
Right? Very good. Which way am I going to number from? 1, 2. My first point of substitution is at carbon 2 if I go left to right. If I go right to left, it doesn't occur to carbon 3. Notice again, it's the first point of substitution. It's any substitution. You don't have to go to the same substituted group. So I'm going to number using the red. Six carbon chain makes this hexane. I'll take a quick look. 1, 2, 3, 4. 1, 2, 3, 4, 5. I got to look at all the examples, right? Got to look at all of them. I have substitutions at carbon 2, carbon 4, and carbon 3. I got bromo, chloro, methyl. I alphabetize. 2 bromo, 4 chloro, 3 methyl, hexane. See how long again? If you want to see this IUPAC naming at work, when you're in the shower, take a look at the back of your shampoo bottle. You'll see it. You'll have names that are like this long that they fit on a shampoo label. They make them very complicated, right? Or sometimes they'll just give it some short name that you can't tell what the structure is. If you put the name in IUPAC, the name's out there for everybody. Anyone who can read IUPAC knows exactly what that structure looks like. And if that ingredient is proprietary or important to their profits, then they'll, give it some little stupid name, and then they'll put that on some copyright or patent or something, so you won't be able to look at it. What is it?
2-fluoro-1,3-dimethyl-pentene.
What do you got?
I have 3-fluoro-2-methylpentene.
That's what I would have. Look at it.
Oh man.
Yeah, this is not one methyl, right? You can't have one methyl. You just increase your chain length by 1. Longest chain, 1, 2, 3, 4, 5. 1, 2, 3, 1, 2, 3, 4, 5. It doesn't matter. If you have a long chain length of 5, then you can count it 2 different ways. Like, let's see, our 1, 2, 3, 4. I could go here for 5, or I could go here for 5. It doesn't matter. It won't change the name. Okay? So if I look at this, what's my longest continuous chain? It's 5. I can only number it in 2 directions. If I number this way, my first point of substitution is at carbon number 2. If I number it the other way, 1, 2, 3, my first point of substitution comes in carbon 3. Notice that it's continuous chain, you guys. You can't have one methyl. Doesn't exist. One methyl would just increase the chain length by 1 more carbon. 1, 2, 3, 4. 1 methyl butane. No. It's just pentane. You just increase it by 1 more carbon. So we're going to number this. You see how your perception, how you're looking at it, that's where it gets crazy. 3, 4, 5. I have F and methyl, fluoro and methyl. Fluoro comes first. This is 3 fluoro, 2 methyl, pentane.
You don't count the, because there's 2 methyl, but you don't count the other one because it's not on the chain, is that why?
This methyl right here,
The one to the right?
Isn't really methyl.
this methyl right here,
No.
what methyl?
Is that
One? This methyl? There's only 1 methyl. The other ones are CH3 in the main chain.
okay.
Like, if I had something like this, let me write this a different way for you. Do you see it now? Here's your main chain. You have a fluorine and a methyl hanging off. It's just written a little bit different. Exact same structures. Okay? Okay. So, other alkyl groups. Let's look at ethane. C2H6. Ethane. Look at my little white ball here. Can I make that appear at every other place by simply manipulating the molecule in space? Yes, I can. Which means all of the 6 hydrogens on ethane are equivalent. So it doesn't matter which one you remove when you create a point of attachment to attach ethane to a larger molecule. What would the alkyl group be? What do you think we call it? Ethyl. Ethyl. You can throw in a methyl. What is this? What are we looking at?
Is it 4-ethyl 3-methylheptane?
Yes, it is. Yes, it is. Longest continuous chain of carbons, what is it? Got a whole bunch of branch points on this, don't we? We got to check them all. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. So far, 7's the highest one. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And if we go straight across, it's 7. Good try. 1, 2, 3, 4, 5. And we've got to look at them all. Numbering our carbon chain. 1, 2, 3. That's our first point of substitution if I start from the left. 1, 2, 3, 4. My first point of substitution if I start from the right is at carbon 4. What do I have? What is that? Ethyl. It's ethyl. It's an ethane minus 1 hydrogen. It's ethane minus 1 hydrogen, C2H5. Methyl here, alphabetizing, 4-ethyl, 3-methyl, 7 is heptane. Everybody got that? It gets a little confusing, right? Because you see the bromines and the chlorines and the iodines and the bromines, they jump right out at you. You say, oh, they're substituted groups. But when they're all carbons and hydrogens, it kind of seems all mixed together. So you have to be able to see this stuff. You have to look at it hard when you see it.
When you're making sure which is the longest parent chain, let's say you're going from left to right to the ethyl, would you count 1, 2, 3, 4, and then 5, 6? And then start from there. 2, 3, 4, and then up 5, and then 6? Is that how you do it?
Yeah. But that's only 6. And
Right,
7's the
right.
highest.
Yeah.
You got to go this way. You got to look at this one. 1, 2, 3, 4, 5.
So like,
That's
so maybe if there's like I think propyl or whatever.
I'm doing that
you-
next.
You would count that in that, so then that would be 7.
Yes.
And so it could be 7
Now
either
would be
way.
a problem. Yeah.
Okay.
That could get messed up.
Yeah. Absolutely. But if you can count 7 2 different ways, it doesn't matter.
Sure.
It'll give you the same name. Okay. Since you brought it up. C3, propane, right? C3H8. I still have one of my hydrogens labeled. Can I make that hydrogen appear at all of the other positions by rotating the molecule in space? Let's make it appear here. That was easy. How about here? Yep. How about on the other side? Yep, 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 yep. But I can't make this white ball appear on these 2 hydrogens without physically removing it and placing it on there. What that tells you is these 2 hydrogens are different from these 6 hydrogens. These 6 are equivalent. They're virtually identical. These 2 are identical, but the groups are different from each other. So we have 2 sets of non-equivalent hydrogens on propane, which means if we take the propane and we form an alkyl group by simply removing a hydrogen from the alkane. That creates the alkyl group. Removing one of these hydrogens and using that as a point of attachment is different than removing one of these outer 6 and using that as a point of attachment. We have 2 different alkyl groups for propane. 2 different alkyl groups. We have to identify them. So for propane, we have 2 sets of equivalent hydrogens. The red ones are equal, and the blue ones are equal. Yes. If you remove a terminal hydrogen from propane, that means one on the end. I'm going to call it terminal, not really. If you remove a terminal hydrogen, you have the generic propyl group. You have the alkyl group that we would call propyl. If you remove an interior hydrogen, obviously the terminal ones are the red, got colors to work with. If you remove one of the blue ones, remove an interior hydrogen, you get the isopropyl. You get the isopropyl group. 2 difference. There is a difference. Here's my propane. I want to create a point of attachment, so I'm going to remove one of these ones off a terminal carbon and I'm going to attach it. I would name it as propyl. If I remove one of the interior ones and use that as a point of attachment, I call it the isopropyl group. Okay? Everybody good? See some examples. Now, notice that as these get bigger, this will be our last one, by the way. We're only going to go to propyl. We're not going to go to butyl. Butyl actually has 4. The normal butyl, the sec butyl for secondary, tert butyl for tertiary, and isobutyl. 4. And I believe pentane has like 9. There's a lot. We're only going to stop. We're going to stop at C3, right? I'll let you breathe a sigh of relief. But as these get bigger, obviously, the molecules that they're substituted on have to get bigger, right? I mean, you can't put a C3 chain on just anything, because that C3 chain could get gobbled up in the longest continuous chain and become part of the parent. So these are getting obviously bigger. What are we looking at?
4 propyl octane.
Yep, 4-propyl-octane. What's the longest continuous chain of carbons? I got 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. I got 8 going both ways, going 2 different ways. My first point of substitution. 1, 2, 3, 4. 1, 2, 3, 4, 5. I'm going to go this way. I got to substitute a group. There it is. It's propyl. It's located at carbon number 4. This is 4-propyl-octane. If I went the other way, One, 2, 3, 4, 5, 6, 7, 8. I still have 8. 4, 5, 6, 7. That's only 7 going this way. I still have a propyl group at carbon 4. It's still 4-propyl-octane. Okay? If I were to look at that using our skeletal formula, I'd have 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. Connect carbon 1, 2, 3. That's what it would look like. Right? Here's our 1, 2, 3 carbon propyl group right there. Here's our 1, 2, 3, 4, 5, 6, 7, 8 carbon chain. Yikes. Everybody see that? Isn't this fun? I'm just going to leave that big thing there. I have an advantage because I just erased the group, right? You guys have to rewrite the whole thing. What is this one? Yes. This is 4-isopropyl octane. Look at the isopropyl group right there. Carbon 1, 2, 3. We are attached at carbon number 2 of a 3-carbon chain. That makes it isopropyl. Notice it looks like a Y. When you see it in the line formula, it looks like a Y. Count them up. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. Still 8, yes.
How can you tell by just looking at, let's say, the line formula, that that's an isopropyl and not a propyl?
Well, you got a 3-carbon chain, right? and you're hooked at the middle carbon.
Okay.
Remember what it looked like before? Yeah,
Yeah.
it looks like a Y.
Okay.
See the Y here?
Okay.
Before, when we came up, it looked like that. So we still had a 3-carbon chain, but we were attached at one of the N carbon,
Okay.
which made it a normal propyl group. And actually, these are called N-alkanes. The straight chain form is called the N-alkane for normal. It means they're straight chains. When you say N-alkane, it means, it means straight. So if you said N-butane, that N stands for normal. And what they're telling you is that they want the straight chain form, as opposed to that other one we did when we were doing isomers, because this is a butane as well. We would name it 2-methyl propane, right, using iodine. But it's also isobutane. Okay, does everybody see that? Lots of memorizing, right? Organic chemistry. Learn it with a pencil in your hand. Write. Every time you see something, recopy it down. You see a name, rewrite it down. You learn OChem with your pencil squarely in your hand. You don't look at this and read it like a book. It's not like English. It's not like any other courses. You learn it by doing. You have to put the pencil on the paper. You have to draw these molecules. You have to write the names. You have to do all of this. Okay? Or it will crush you. You can see, we've only done one, by the way. We're still on alkanes. We have like 13 more functional groups to do. Okay? This is one. Okay? I'm not trying to scare you. I'm just saying, look, this is where it starts. Right? This is when we start doing it. You go home, you memorize these first 10. You memorize these alkyl groups. Because tomorrow we're doing something different. Alcohols, phenols, and ethers, I think. I don't know. I haven't looked at the lecture. Okay? Okay. Everybody good with the alkanes? Lots of practice. Okay. Cycloalkanes. And they're just what you think they are. They are ring structures. Cycloalkanes, these are just ring structures of alkanes. You can take your straight chain alkane. That's my N. Okay? So I've randomly chosen 2, 4, 5 pentane again. All over pentane today. Okay? And these, as these molecules get bigger and bigger, they can flop around and flip around on each other. It's possible for them to flip around and lose 2 hydrogens here. These hydrogens have to go away on the ends, and then they can create a point of contact and close into a ring structure. Okay? Now, rings are considered unsaturated. Okay, you can think of saturated as meaning that each carbon has its maximum number of hydrogens to maintain its tetravalency. Any number less, you see how these terminal carbons are CH3s? They're CH3s. But if you create a ring, you lose the CH3 and it becomes a CH2. Anything less than the maximum hydrogens given by the general formula, CnH2n plus 2, for the alkane, is considered an unsaturated hydrocarbon. So rings are unsaturated because they don't have the maximum number of hydrogens on each carbon. We draw our rings exclusively using the line formula. We call them geometric formulas. So when you look at them, you simply count them up. 1, 2, 3, 4, 5. Normally C5 would be pentane, right? But this is a ring, so we call it cyclopentane. You just stick the prefix cyclo in front of it. What's that? Cyclohexane. Each change of direction is a carbon. And if we were to write that out, it would look like this. Well, I can do the look like this. That's what cyclohexane would look like in an expanded structure. You rarely draw that. Too tedious, takes too much time. When you see a ring, a geometric formula, we call these geometric formulas, put the prefix cyclo in front of the normal alkane name, and you got your alkanes. You can substitute on the rings. Generally, if you have one substitution, you do not have to locate it. You don't have to say, remember, you can start numbering your chain from any place. So in order to number your chain in such a manner that you put the lowest number on the first point of substitution, this one's always going to be carbon number 1, where the substituted group is. So you don't have to say 1-chlorocyclopentane. You can just say chlorocyclopentane. If you have more than one substitution, then you have to start locating them. You have to start locating them. Now, you always want to number your chain in such a way that you put the lowest numbers on both of them. So, you wouldn't start here and say 1, 2, 3, 4, 5. Right? You don't want to do that. And in this case, you can go 1, 2, or you can go 1, 2. Right? Which one do you think you want to pick? Bromine on carbon number 1. Because you have a choice, you're going to alphabetize them, put the bromine first. So we're going to choose the purple. Now you can name this a couple of different ways. You can say 1 bromo, 2 chloro, cyclopentane.
Or without the one?
What's that?
Or can you do it without the one?
Yes. 1 bromo, 2 chlorocyclopentane. This is probably the method that I would choose. This would be the method that I would choose. Alternatively, you could say 2 chloro bromo cyclopentane. 2 chloro bromo. You know what? No, we can't say that. Can't say that. Can't say that. When you have 2 substituted groups, you have to locate both of them. 2 or more. 2 or more substitute groups. Okay? Just recognize it. You know, a little box is a cyclobutane. The pentagon here is cyclopentane. Hexagon, cyclohexane. Okay, what kind of reactions do we get with our alkanes? The alkanes, by nature, are reasonably unreactive. Okay, they're pretty unreactive. They don't do a whole lot of things. But one of the reactions that they do undergo is combustion. A combustion reaction has O2 as a reagent. Combustion reactions have O2 as a starting material. When you combust alkanes, we'll pick methane, plus O2, we're going to add a little heat. Combustion of alkanes always produces CO2 and water. It's a general reaction, just like acid plus base produces salt plus water. The combustion reactions, and they will release energy. In your car, you burn gasoline, that's an alkane, octane. You add a little oxygen, a little fire from a spark plug, and you know it produces energy. It's what moves your car, right? We would have to balance that equation. What would that require? 2 here and a 2 there. But whenever you have a hydrocarbon, alkane hydrocarbon here, and you add oxygen to it and combust it, you will get CO2 and water. The next one is halogenation. Halogenation involves the radical-induced chain reaction, so it'll be a substitution. I think we're probably only going to concentrate on chlorine, maybe bromine. No, it looks like just chlorine. And then we're going to need some form of energy. This is either going to be light or heat. Light or heat. And what we get is a substitution. This actually occurs by a radical-induced chain reaction. It produces radicals, and that's how the mechanism occurs. But you see, we have actually a swap here. One of the hydrogens switches with the chlorine, and then we produce HCl. And that can actually keep going. If you have enough chlorine, the chlorine will hit this again and go to CH2Cl2. And hit it again and go to CHCl2. Hit it again, ultimately it'll go to CCl4. Halogenation reactions. Okay. Pretty much those reactions are going to be memorization. You're going to have to memorize those. Right? Telling you, be careful what you wish for. All right. We looked at alkanes. Let's look at alkenes. Alkenes. Alkenes are unsaturated hydrocarbons, I'll spell that. the general formula I'm gonna write it over here. CnH2n. Alkenes are unsaturated hydrocarbons with a general formula CnH2n. Unsaturated means that it contains a carbon-carbon double bond. Now, in order for it to satisfy this general formula, it can only contain one. Okay? It's possible to have multiple double bonds in alkenes. They're called dienes, trienes. You get it? Di, two enes, double bond. But to satisfy that general formula, it can only have one double bond. If it has two, it's not going to fit in. Again, they're hydrocarbons, so they contain only hydrogen and carbon. We can have the first couple ethene propene butene, etc., etc., etc. Now, how come I don't have a methene double bond? How come I don't have a methene member?
The structure is before.
Well,
Because it couldn't satisfy the formula.
and what do alkenes possess? Carbon-carbon double bond, right? And methane is only one carbon. So the first member of the alkene class is ethene because you have to have at least two carbons in order to have a carbon-carbon double bond. Okay? Butene, pentene, all the way down. Notice alkenes end in ene, and you know when you see the ene ending that you have a double bond in there, at least one. Now our rules for naming are all the same, except for one thing. We now number our carbon chain with preference given or priority given to the carbon-carbon double bond and not substituted groups. We don't care where the substituted groups are. We give, this is really our first functional group. Alkenes all contain at least one carbon-carbon double bond. Alkanes are really designated or identified by their lack of a functional group. They really don't have any common structural features other than the formula, CnH2n plus 2. Alkenes, however, do. And you can see them, you can identify them. So when we look at the structural formula for ethene, the first member, notice my geometry's changed a little bit because the geometry around the double bond is different than the geometry around carbon-carbon single bonds. If I look at propene, notice here, it doesn't matter where I put the double bond. It's still going to involve carbon number 1, right? Let's look at butane. Notice I'm maintaining my tetravalency. All of my carbons still have 4 bonds. Notice when I get to butene, I can put the double bond in two places. I can put it between carbon number 1 and carbon number 2, or carbon number 2 and carbon number 3. I do number my carbon chain with preference given to the double bond. And it's always the first carbon of the double bond that's used to locate it. So if I number my chain in this way, this is 1 butene. I have an ene, a double bond, that begins at carbon 1, and it's understood that it goes to carbon number 2. This one would then be what? That's right. 2 butene. So any carbon chain of 4 carbons or more, you have to locate where the double bond is. You do not have to locate it in ethene. It's obvious. You don't have to. It involves both carbons. In propene, you do not have to locate it because either way it's going to be 1 propene. This is 1 propene. So is that. Let's put another hydrogen. That's 1 propene. I just number from the other side. But if you have a carbon chain of 4 or more carbons, you must locate the double bond. You have to. You have to. Other than that, everything is the same as our rules develop for alkane naming. I'll show you some examples. Let's see. Notice my double bond. See, it looks funny, right? Because the H's are there. But if you expand it out, you see that each carbon in my double bond has an H. My expanded formula here would be verify there. CH3, CH, double bond, CH, CHCl, CH3. We follow all of the same naming protocols, except we don't care about substituted groups. We number our carbon chain with preference given to the double bond. Whatever puts the lowest number on the double bond, that's the one we use. What is this?
Is it
4-chloro-2-pentene, yes. I don't even care about this chlorine. I'm numbering my chain to put the lowest number on the first carbon of the double bond. 1, 2, if I go that way. 1, 2, 3. If I go the other way, I'm picking this way. I don't care about the fact that the substitution is on carbon 2. Preference isn't given to substitutions anymore. It's given to functional groups. I have a 5-membered chain, pentane. I have a double bond. pentene. The double bond is at carbon 2 to 3. 2 pentene. Chloro at 4. 4 chloro. 2 pentene. Everybody see that? They're all the same. Locate the double bond, number your chain. The substituted groups are going to fall out where they fall out. Okay, again, no preference given to ascending or descending. That's what it is. Okay. Alkynes. Alkynes these are unsaturated hydrocarbons with a general formula of CnH2n-2. Notice for the alkanes, we had CnH2n plus 2. Then the alkenes, we went CnH2n, and the alkenes had at least one double bond. And then for the alkynes, we had 2n minus 2. In this case, the unsaturated means that it contains at least one carbon-carbon triple bond. So you could say that for every pair of hydrogens that I lose, I generate an additional bond. And you would be correct indeed. Here, I have no double bonds, no multiple bonds. Here, I have one double bond, but it costs me 2 hydrogens. Here, I have a triple bond, and it costs me an additional 2 hydrogens. So this one actually has 4 different difference of 4 hydrogens from the alkane to the alkyne. 2 for each bond. Again, our first couple of members. Ethyne, C2H2. Notice if N is 2, 2 times 2 is 4, minus 2 is 2. Ethyne, propyne, H4, butane. If I look at ethyne, notice that in the alkynes, the functional group is a carbon-carbon triple bond. Carbon wants to have 4 bonds, each carbon. So the requirements of the carbon-carbon triple bond take up 3 out of the 4, which means each carbon involved in a carbon-carbon triple bond only has 1 bonding position left. The alkynes had 2. We're going to see a consequence of that in just a minute. Okay? This is ethine. Unfortunately, I don't think I've ever seen it as ethyne. No. This is known almost exclusively by its common name, acetylene. Okay? The carbon-carbon triple bond is the shortest and strongest of all the carbon-carbon bonds. The carbon-carbon single is the biggest, the carbon-carbon double is smaller and stronger, and the carbon-carbon triple is the smallest and strongest of all. So when you break that triple bond, you get all that energy back. And it turns out, for ethine or acetylene, that energy is strong enough to cut steel. This is a gas that's used in acetylene torches. It cuts steel. Okay? What's the problem here? Anybody see a problem? I see a big problem. Acetylene ends in ene, and we could easily mistake that for an alkene. It's not. Okay? Got to put that one in the back of your mind. That's just a common name. Acetylene. Propyne. As usual, with a C4 or greater, we have to locate the triple bond. I should have put that off to the side. Let me put that off to the side. We don't have to place a name on it. It looks unusual to see the carbons in the middle with no hydrogens on them. We've seen that before, but we saw chlorines or bromines or something like that attacked. But the carbon's tetravalency is still maintained. This carbon has 1, 2, 3, 4. This carbon 1, 2, 3, 4. So it's got no room. It's got no room. This would be 1 butine. This would be 2 butine. Just like our alkenes, we have to locate the triple bond in molecules C4 or greater. We have to locate it. C3 and C2 we don't. Everything else is the same. Priority is given. Numbering our chain, our priority is given to the carbon-carbon triple bond. What is that?
4, 5 dichloro 2 pentine.
2 pentine, right? Yes. We don't care about the substitutions at all here. What we're looking at is which way do I number my chain so that the triple bond takes the lowest number? So I go 1, 2, carbon number 2. I start from the other side, 1, 2, 3. I'm going to go this way. I have 2 substituted groups. They're chloros. They're on carbon 4 and 5. This is 4, 5 dichloro 2 pentyne dash right there. Going the other way is easier. Given the name and drawing the compound is much easier, right? I have a pentyne. 1, 2, 3, 4, 5. I have 2 YNE. Carbon 1, 2. There it is. YNE means triple bond. I have a triple bond at carbon number 2. It begins at carbon 2 and goes to 2 to 3. That's understood. It always goes in order. I have chlorines at 4 and 5. 1, 2, 3, 4, 5. It doesn't matter that I put one chlorine up and one down. There it is. Given the name is somewhat easier. All right. Let's go back for a minute and revisit our alkenes. If we look at our alkene, this is ethene. Okay? The first thing we notice about an alkene is that we don't have free rotation around the carbon-carbon double bond. You don't have free rotation around the carbon-carbon triple bond either. It's only the carbon-carbon single bonds that have free rotation. So this is locked into a configuration. If you have both carbons with a substitution, I have an alkene here, ethene. I have another one here. And I've chosen to substitute both carbons. Let's say I put chlorines on both of them. Okay? Chlorines on both of them. The only thing I need to do to convert these two structures, one into the other, is simply rotate around the triple or the double bond. But I can't. The carbon-carbon double bond does not have free rotation and therefore divides the molecule into two halves. You can think of it as top and bottom, right, left, it doesn't matter. If both carbons are substituted, they have something on them other than hydrogens. The substituted groups can end up on the same side of the double bond or they can end up on opposite sides of the double bond. These are clearly two different structures. So we have to have two different names for them. If they're substituted on the same side, we call them cis. This is cis 1,2 dichloroethene. Cis 1,2. Cis meaning same. This is trans. 1,2 dichloroethene. Trans because they're across. This double bond creates a rigid plane. They're on opposite sides. Trans means across. Transatlantic, across the Atlantic, what have you. If the substitutions are on the opposite sides, it's trans. If they're on the same side, it's cis. So back when we looked at 2-butene if we look at these in the line formula, they look like this. Two butene actually has two geometric isomers. That's what we call cis and trans. Geometric isomers. So if you see cis and trans, these are geometric isomers. They have the same formula, i.e. isomers, but different geometries. Geometric isomers. 1, 2, see the double bond? They're on opposite sides. Here's my double bond. My substitutions are here and here. That's opposite. This is trans 2-butene. Here's my double bond. Where are my substitutions? They're on the same side. This is cis 2-butene. Cis and trans, geometric isomers. Only carbon-carbon double bonds have cis and... I want to say that because rings can have them too. But for us, we're going to say alkenes are going to be the only source of cis and trans isomers. Carbon-carbon triple bonds do not have cis and trans isomers. Single bonds do not have cis and trans isomers. Rings do. Oh, we're not going to get into that. Okay? What kind of reactions? What kind of reactions do we get with alkenes? Alkene reactions. Generally, these are going to be an addition reaction. Addition reaction. Most of organic chemistry can be broken down into one of 3 or 4 types of reactions. You have substitution, you have elimination, you have addition. And then another one in there is radical mechanisms. Addition reactions, the general formula, okay? General form is that you have a carbon-carbon double bond and you add a substance to it, AB for example. We'll see what that is in a minute. And each one of those adds to one of the carbons in the double bond. Okay, it's an addition reaction. You're adding those elements to the molecule. We have only 1, 2, 3 types. 3 types for your viewing pleasure. Okay, the first one is hydrogenation. I'm going to erase this so I can get it all on this little board. It really hurts that we can't use that board. Hydrogenation is the addition of H2. It's the addition of H2. We have our carbon-carbon double bond, and we're going to add H2 hydrogen to it. Now this does require a catalyst. Usually it's just palladium or activated charcoal. It's something that allows the 2 reagents to get together, the H2 and the alkene together. And you're simply going to add a hydrogen to each carbon of the carbon-carbon double bond. Hydrogenation. What does that create, you guys? It takes an alkene and makes what? Alkane? Makes an alkane, doesn't it? It takes an alkene and makes an alkane out of it. Any reactions that jump across functional groups or classifications are important. Okay. Incidentally, anything we're doing here with alkenes can be done with alkynes. You can hydrogenate an alkyne. The only thing you have to do is you have to add 2 moles of H2, because 1 H2 will break the bond, and you have 2 extra bonds here. So you need 4 hydrogens, right? Again, it'll require a catalyst, and the added hydrogens will show up like so. You need 1 H2 to break a bond. 1 mole of H2 to break a mole of bonds. So if you have a triple bond and you want to break that down to single, you got to break 2 bonds, which means you need 4. Okay? Any of these reactions that we're showing for alkenes will run with alkynes if you double it. You got to double the number. Halogenation. Halogenation, this will be the addition of Cl2, Br2 primarily, Yeah, we're going to stay with Cl2. Cl2 will be R2. That's usually what it is. Okay, the I2 is too big, the F2 is too small. So Cl2 and Br2. In this case, we're going to take our carbon-carbon double bond. Notice that I'm not putting anything. I'm not putting anything on our carbon because it doesn't matter what's out here. It doesn't matter if these are long hydrocarbon chains or hydrogens. It doesn't matter. The reaction's happening right here. The alkene is dominating the reactivity of the molecule. So I'm going to show you Cl2. And all we're going to do is add a Cl to both carbons of the double bond. Okay. Lastly, we have hydration. What do you do when you hydrate? Add water, right? Add water. That's what we're going to do. Addition of water. We're going to have our carbon-carbon double bond. We're going to add water, H2O. We're going to think about water as being HOH. So let's think about water as being HOH. That's H2O. This will require an acid catalyst. Notice from our lecture last time, H plus, brackets. The brackets mean molar concentration. This is acid catalyzed. And because we think of water as H and OH, we add a hydrogen to one of the carbons and an OH to the other carbon. And our product looks like this. I'm going to move it out even more. It's nothing more than a typical addition reaction, except we're adding H to one carbon, OH to the other. Okay? These are the reactions that you should know for alkenes. Okay? Only got one more thing, right? It's short. Okay, lastly, benzene. Aromatic carbons. I'm sorry, aromatic compounds. I'm getting tired. Aromatic compounds. Aromatic compounds contain benzene or its derivative. We're going to say benzene. Benzene has a formula C6H6. It is a six-membered ring with alternating single, double bonds. Get another one. I need one more. This is benzene right here. It's alternating carbon-carbon single and carbon-carbon double bonds. Its structure was discovered by a guy named Kukle, and it is said that he had a dream the night before of a snake eating its tail, and that's how he came up with the structure. Okay, I don't know if drugs were involved. Right? Look at how flat it is. This is a remarkable molecule. Remarkable. It has unbelievable solvent properties. I used it in graduate school. When I was working with proteins and I could not get them to dissolve, I just put a couple of drops of benzene in, dissolved them. Okay? It's a remarkable solvent, but it'll kill you. Sorry. Right? It's a known carcinogen. It's very, very bad for you. Right? But it's still a pretty cool molecule when it comes to solvent and how it looks. With modern instruments, we should be able to tell these alternating single and double bonds. Because a carbon-carbon double bond is shorter than a carbon-carbon single, we should be able to perform structural analysis on this and see 3 carbon-carbon singles and 3 carbon-carbon doubles. You don't. Okay, you don't. What you actually see is 6 identical carbon-carbon bonds, almost exactly in the middle of what a carbon-carbon single bond should be and a carbon-carbon double. What you have is basically 6 identical 1 1/2 bonds. It's crazy. If you look at the structure, since you have alternating single, double, single, it's like, who's to say where they're at? Are they here or are they there? So you can have 2 possibilities. These forms we use to justify the reactions and to justify observed products when we use benzene. The actual, more realistic way to represent benzene is with a hexagon and an inscribed circle. An inscribed circle in the hexagon. Now, if a compound contains benzene or its derivatives, it jumps right out at you. You can see it, you can tell. And when it was first discovered, all of the compounds that contain benzene stunk. I mean nasty stink. Okay? Like mothballs. Have you smelled mothballs? They stink. That's aromatic. Or how about airplane glue? That's toluene, that real acrid, nasty stink. Rotten fish. Benzene, usually aniline type derivatives. We're going to do a lab and we're going to use some of that stuff and it'll run you right out of here. It's just so nasty. They're aromatic from the term aroma because they had a really pungent, nasty smell. Well, there are hundreds of compounds that have benzene in it that don't stink, but the name stuck. Okay? Aromatic doesn't necessarily mean that it has a strong aroma. Aromatic now means that these compounds exhibit this extreme, surprising stability. Benzene is relatively unreactive. In fact, all of the alkene reactions that we just studied, all those addition reactions, benzene won't even do them. Won't even undergo those reactions. It's too stable. Okay? And this is a result of the aromatic character. And there's a couple of reasons why, but we don't want to get into it. Just know for now that aromatic characters contain benzene and that you need to be able to see and recognize the characteristic 6, the hexagon system. This is actually a 1, 3, 5 cyclohexatriene. 3 enes. It's a 1, 3, 5 cyclohexatriene. We're not going to name it that way. We'll name it benzene, right? It's so much easier. Yeah. There are a few forms that you should know on benzene. You can substitute. Okay? Those are in your book. But you can name benzene in basically two different ways, or benzene-containing compounds. Okay? There's a couple of different ways, and since it's a multiple choice exam, I don't know which ones are going to be on there. You can name it as a benzene derivative, and because there's only one substitution, you can just call it methylbenzene. Methylbenzene. You can just name the attached group and follow it up with the word benzene. Or you could see this as toluene. This is a major chemical in airplane glue. This is what stinks in airplane glue. Okay? You have to know. You have to know them both. I'm sorry. There's toluene, phenol, aniline, and benzoic acid. You just have to know. Just memorize those benzene derivatives on 718. Okay? The di-substituted benzenes and two or more substituted groups on benzenes, we handle them just like we'd handle cycloalkanes. You number them, you alphabetize them, the whole bit. Yeah.
So what would be the other name for the phenol? Would that be like
Hydroxybenzene. Hydroxy.
hydroxy?
Yeah, we don't call the OH hydroxide, we call it hydroxy.
Yeah.
You'll almost exclusively see that, though, as phenol.
Okay.
It's phenol. You could call it hydroxybenzene, but... Okay. Pretty much just memorizing and recognition. Right? We're not doing any reactions involving benzene, so benzene's coverage on the exam is going to be limited just to naming and your recognition of it. Okay?